binary trees. Consider all the leaves of a binary tree from left to right order. The values of those leaves form a leaf value sequence. So these are the leaves from left to right. For example, in the given tree above, the leaf value sequence is 6, 7, 4, 9, 8. The two binary trees are considered leaf similar if their leaf value sequence is the same. Return true if only and only if the two given trees with the head root 1 and root 2 are similar. So for example, over here, these two are in the same exact sequence. The leaves in them are in the same exact sequence. So, and here it's false, because even though we have the same values at the same level, the sequence isn't the same. So we can easily see that we need to do a depth first search, going down and then up, and going up and then right, down. So we can easily do this with a BFF, a DFF, DFS problem. A depth first search. So from left to right. That's it over there. And so return true if only the two values are the same. So let's keep this one in mind. This is going to be our solution. So let's make a function called getLeads and make our list, put our list there. You get, a method, you get leads. Let's put our root inside as parameters so that we can use any of the two. Leaves equals to leaves. Let's make our DFS function def.dfs. Let's make this node. So now let's make our base case. So base case will make our function come to a stop. Our recursion come to a stop. So if none, node is none. Return none. So now so what's next now? So how will we be able to define a node with a leaf node? So a leaf node will not have a left child or right child like these above them do. So if node dot left is none, and node dot right is none. Let's add it to the leaves. Leaves dot append our node the value inside it. Let's make our recursion function to go to the left node dot left and node dot right. So now the nodes will keep going left and right until we hit this or this. Then we will add this to this. So now the move is to let's make our DFS our root. Return leaves. So now let's go to under our leaves similar function, and now let's define our left leaf 1 will be leaf. I'll just put 1 over here. Leaf 1 is equals to get leaves, and then our input root 1. Leaf 2 will be our leaves, not leaf. Leaf 2 is equals to or get leaves root 2. So now that's it for this, and let's return the function. Function equals to leave leaves 1 equal comparing. This will enable us to get return leaves 2. Let's see if there's any syntax errors that need to be fixed or mistakes, and that should work. Let's see. Yes, and it's all been accepted successfully. Now let's submit it and see if it's going to pass all cases. And it's been able to pass all cases. But this is our iterative method. Our recursive method. Recursive method. Now let's move to our iterative method def the get leaves dot root. So now iterative method approach. So now let's copy and paste this so we can keep an eye on exactly what we need to return. So get leaves. So now let's make our list. Let's also name it leaves. Let's call let's name our start and put our root inside it. Root. So while we have our start node equals to start dot pop. If node is none, no, if node dot left is none, and node basically is the same exact node dot right is none. Let's append it to the lease dot lease lease dot append dot node dot value. So let's add the value to it. So now let's go to the right first. If node dot right, if we have a right node, we're using a stack in this case. Let's pop it. Let's append it to the start dot append it to start to append node dot right. If you have a node dot left, start dot append node dot left. So now we have all of these inside them. Now, if it doesn't, and this it doesn't keep going. If this is none, then none. Add it. If this is none, so if this is, if you have a node to right, while we have a node, if node has a right, add it to the stack. If it has a left, add it to the stack. So we pop the last in first, and then we come over here, add this one to the stack, and then add this one, and this one gets, if it gets popped up, when it gets popped up, it gets added to the list. So that's our so now let me copy and paste these. And copy these, paste these. Is it pasted? No. What? Okay, I have to copy this one. Okay, so now let's return our leads. So while we have a loop, well, so now this we go we'll start while we have a start. Keep going, do this. Let's run it and see if it works. And it's been able to pass all cases. Let's submit it to see if it will pass all cases. And it's been able to pass all cases also. And now let's get into our time and space complexities. Our time complexity is O of m plus n. Our space complexity is O of h plus h. H being all being height. H node gets more efficient approach for very deep trees. More of the approach than recursive approach for each node being visited once on every 3. And that's it for this problem. It's somewhat easy, but we have been able to find out if both trees have similar nodes.